Let's take a little peek at nuclear chemistry. The main topics we're going to talk about in this chapter would be things like radioactive decay. So that's by far the most important part of this chapter. So if you can't learn anything else, that's what you want to focus on. When I say radioactive decay, I'm talking about alpha decay, beta minus, beta plus, and that sort of thing. So those are the things you're most likely to see problems on. And then the half-life problems, which are going to be just like the ones that we did in chapter 14 in kinetics for first order, so you don't even have to worry about zero or second order in this chapter, just first. The problems will be just like that, so you might want to review those from chapter 14. Those are the other ones that you're kind of likely to see. They'll tell you you've got such and such an amount of nuclide, and then 3 hours later, how much would you have left? So that's the next most common thing you'll see. And then that's probably going to do her for the final exam. For my exam, you'll also need to keep going, though. So, for example, you'll want to be sure you know how to do mass defects, which are not hard. Once you see the pattern, it's the same thing for any element. We'll talk about that. I don't even want to mention it right now or get started on it because we're going to talk about it in detail later. And then we'll also talk a little bit about how to figure out the rims that you got exposed to if you got in an accident and how damaging it could be. And then there's a couple of other topics that we're going to talk about. Now, before we start off, there's a few things that I pulled out of my lecture slides that are like the full set. The ones on Canvas, because there's just no way on earth we could have time to do that. I'm trying to keep these under about an hour from now on, and I think I can do that, or roughly an hour. And there's several reasons. It's not I'm lazy. It's because the bigger they are, the longer they take to process. And I mean, it's harder for you too because you have to sit there and watch them. So I'm trying to condense these a little bit, and I'm trying not to talk too much. So let me just give my usual credits. Credits to Zumdahl. I think most of these slide sets were from Zumdahl originally, and then I kind of converted them over to Brown LeMay. And credit to Brown LeMay, and then also to Mr. Mack's website. The lecture slides here have been enlarged upon a great deal by myself, although a lot of the stuff that I had put in has been taken out. So I recommend, if you have the time, if you're interested, maybe not before finals, but after, if you want to just go back through the longer version and go through some of the things just for your information, but unfortunately I won't have time for that. So let's go to the next slide, and then next. All right, so we've already talked about this. So some of these things down here, well, we'll talk about all of these. Yeah, we'll talk about all of these. Some of them not very much, but a little bit. Next slide. Okay, so what I want to do at the very beginning here is I want to help you to understand basically what happens with these radioactive processes. So there are, it turns out, 4 different kinds that we're going to talk about, actually 5, but one of them is very straightforward. It's just gamma decay. That's just when you send off an energetic photon in the gamma frequency. So basically the ones that we're going to worry about are alpha decay and then the 3 different kinds of beta decay. So to get to that, we need to just review from 1311 for a moment. So what we see here is that, remember from 1311 that the Z number here at the bottom, and it doesn't always have to be at the bottom, so you have to really be careful, because some charts, for whatever reason they may have, will flip these, they'll invert them. But mostly you put them at the bottom. So the Z number is telling you what the atomic number is. That means how many protons. The top number tells you not the number of neutrons. It tells you the number of protons and neutrons. So if you want the number of neutrons, you have to subtract A minus Z. When you get into nuclear chemistry, they usually won't write the Z. And the reason for that is when you write whatever X is, like if it's Fe, iron, then you know what Z is. You can just glance at a chart. So they usually don't even write it. For this chapter, though, we will. Okay, so again, for the way they have it written here, the thing on the bottom is going to be the number of protons. The thing on the top, A, is going to be the number of protons and neutrons. But check it and be careful, because some charts flip them. So the way you could tell that is you're looking for the smaller number is going to be the Z number. All right, let's go to the next slide. So whenever we have this kind of decay, it's different from everything else in chemistry that we've studied, and that's because it makes something different. Like when I was a grad student, I did a lot of work in gold. When gold decays, it produces platinum, or it can decay in different ways. So it's actually going from one thing to another, which is like the old alchemist dream of converting lead to gold. Well, you can't do that. The reason they thought maybe you could was because they were both heavy. You can't go from lead to gold. Gold, I mean, lead, first of all, is stable, and it doesn't decay. But it's way away in the chart from gold. But you can change things from one thing to another. So whenever you have something like that, it goes by different names. And so this is one of the things you'll want to watch, because they tend to ask this on the final exam. So there's one thing that's called fusion, there's one thing that's called fission, and there's one thing that's called a nuclear transformation. And then it all kind of can be wrapped up as being called radioactive decay. So I'll just mention this right now. If I think of it, I'll mention it again later. Fission usually is going to be when you've got something like uranium that's very large. It's a very large atom, like huge. And you hit it with like a neutron and it splits it into two big chunks. Fusion, on the other hand, usually you'll start with something tiny, tiny, like hydrogen or helium, and you'll add it to another one. And so you'll wind up going from a helium and a helium to whatever, you'll fuse, or a helium and a hydrogen, and fusing them. And that's what you should watch for, because what they'll do on the final is they'll ask a question like that. They'll say, okay, whenever you've got, like, let's say hydrogen plus hydrogen, what kind of reaction is that? And then the answer choices there are going to include things like fission and transformation, but those aren't the right answers, because usually when they're talking about fission, they're talking about, as I said, something very large, not H. So I mean, there's no way you're going to have fission with H. It could be considered a transformation, but usually when they're talking about a transformation, you're going to be looking for something like when you're starting off with, say, nitrogen, and you're converting it to oxygen, which is one of the things that's mentioned here. Next slide. Okay, so if you look at the chart, if you read up the chart, or down the chart actually, down and across until you get to atomic number 84, which is polonium, once you get up to 84, things above that are generally unstable. That does not mean that things that are lighter than 84 protons never decay, because they do all the time. I mean, all the way down to beryllium. But it's just that when you get above 84, they get really unstable. And so what they'll typically do is they'll start to decay by an alternating pattern of alpha decay and beta decay, which we'll look at later. There's an area, well, let's hold off on that. So whenever you start going up the chart, like if you plot on one side, you plot the number of protons, and then across the x-axis, you plot the number of neutrons. Down at the very beginning here, when you're dealing with things like hydrogen and helium, up to about n equals, I don't know, 10 or so, the number of protons tends to equal the number of neutrons, and there's a reason for that, which will, maybe I'll try to remember to talk about it. But then the higher you get, you have to have more neutrons. You have to have more neutrons because that's required for stability. So it's not going to stay linear. So as it says at the bottom here, the neutron-proton ratio will get to be larger than 1, and it will keep getting larger and larger. The reason is because you need more neutrons to stabilize the nucleus, and the reason you need to stabilize the nucleus is because protons have a +1 charge and they repel each other. So if you think about it for a minute, if you think about an element that, let's say, has 84 protons, like they mention here, that's 84 positive charges. What's keeping those things from blowing up? Because they're all repelling each other. Well, the answer is the neutrons. And just the short answer is that they're all made up of quarks, but the quarks in the neutron are, I mean, without going into detail, they're negative, negative, and positive, whereas the quarks in the proton are positive, positive, and negative. And so what you can actually do is line them up so they effectively cancel each other out. As long as you have at least one neutron per proton, However, if you get really big atoms, they have to have more than one. Next slide. So I said I wouldn't talk too much, and I already am. So I'll try to knock it off for the rest of this slideshow. So certain combinations of protons and neutrons seem to confer special stability. You could see a multiple choice on this on the final. Even numbers of protons and neutrons are often more stable because they're paired. So in some ways, protons and neutrons act like electrons in that they're more stable when they're paired. So if you have either an even number of protons or an even number of neutrons, or even if you just have an even number of the total A numbers even, then that means it's going to be more stable. And then also there are some numbers that are called magic numbers. Next slide. And those are 2, 8, 20, 28, and so forth. So you don't have to remember these, but just be aware that they may ask this on the final exam. 2, 8, 20, and 28. Where this could be either the number of protons or the number of neutrons or the total. They're called magic numbers because they're extremely stable. And it's because of the way their orientation is in the nucleus. So let's move on because we don't want to dwell on this. All right, so this is important. So this is a chart with protons, and they've actually got the neutrons over here, and they've got the protons on the x-axis this time. So what's happening is at the beginning down here, you've got about a 1-to-1 relationship, but as you go up above about here, about number 20, or even lower than that, then you notice that this red area here, this area right here, veers away from that straight line. Now that straight line, that red line, is if you had 1-to-1. So it's okay to have that 1-to-1 at the very beginning at the bottom left of the chart, but the further you move to the right, the further it veers away, because you need more neutrons per each proton to keep it stable. And this area that I marked here that's red is called the island of stability, or the zone of stability, and that is where things are stable. They don't tend to decay. So that means that since all of these blue and red dots all represent an actual nuclide, and when I say a nuclide, I just mean basically a nucleus of some atom isotope. These things all represent actual nuclides that are found either in nature or in the laboratory. So that means that the things over here in blue and the things up here on the top here in blue are not stable. So they'll tend to do decays that get them to move either, like if you're over here, then they'll decay to try to get over here to the island or the zone of stability. There's actually two different things that are actually not quite the same, but they kind of mean the same thing. There's an island of stability that isn't shown on this chart, but it would be up here at the top. Things here have too many protons, so they tend to give up decays that will reduce the number of protons and add to the number of neutrons to go in that direction, and all of them are trying to get in the middle. So does that mean that eventually they all will get in the middle? No, probably not in the foreseeable future because there are so many of these. But that's the basic thing that's driving this. However, there's another thing that drives this, which is the fact that we tend to have something called alpha decay once we get past atomic number 84. So for atomic number 84, that's right here, if we bring that up, we see that right about here, everything is unstable, right? So if you draw a line right here, I mean, you're not going to be asked this on the test, but if you draw a line, everything to the right and above that is going to be unstable. So it will not only need to get to the center, but it'll also need to reduce its mass, if you will, by giving off alpha particles. So up at the top here, you have especially alpha decay, this area up here. Next slide. So let's look at the types. There are mainly 4. There's actually 5, but we're not going to worry too much about the last one. Next slide. So alpha decay is pretty easy. You just lose a helium nucleus out of whatever you start with. So you're going to produce whatever you started with minus 2 protons and 2 neutrons, and you're going to wind up with an alpha particle, which again is just a helium nucleus. So notice here we're starting with uranium-238, and we're producing something that's going to be 2 less here. So that's going to drop to 90, and that's going to drop 4 to 234. Now, the reason the atomic number only drops 2 is because the helium nucleus only has 2 protons, so you're going to drop from 92 to 90. And then you're also going to lose out of your mass, you'll lose the 2 for the protons and also 2 for neutrons. So it goes down by 4, so it would go from 238 to 234. And you also produce this, what is called an alpha particle, which is a helium nucleus. In other words, it's a helium that doesn't have the 2 electrons. So whenever you've got alpha decay, the atomic mass will always decrease by 4, and the atomic number will always decrease by 2. And this is especially true for the things that are above atomic number 84. Usually it will occur in alternating steps with beta decay, which will, I think we have a slide for that. Before we go to the next slide, I just want to mention that almost all of these things that we're talking about here will have other things going on besides just what we've written. Like this one, for example, this is what we want to remember from this. But that's not the only thing that's happening, because there's probably going to be other things like gamma rays, for example, which we're not including when we write this, and neutrinos could be produced, and other particles could be produced, subatomic particles. So what we're worried about right now and for this class is just the main thing that's happening, but just be aware that all of these things will involve other things going on as well. Next slide. All right, now the beta is the confusing one. There's 3 different kinds. One of them goes in one direction, and that's the beta minus that we're going to talk about now. And it goes in the direction of neutron to proton. So basically for beta minus, we're taking a neutron and turning it into a proton. So a neutron, if you want to think of it this way, is like if you took a plus and minus charge and shoved them together, which that's kind of the way it is if you look at the quark structure. Anyway, so in this case, what we can imagine happening is that the proton part of it is emerging from the neutron and giving off the negative part, which is the electron, only it's shooting that electron out. Now, this actually doesn't make the mass less. Well, actually it does. Okay, sorry. It does make the mass less, but not by very much. So protons actually do weigh just a little bit less than neutrons. So what's happening as far as the net result in this atom is that you're going to wind up with 1 more proton than you had initially. So for example, this probably wouldn't happen, but if you started with carbon, well, it might. If you started with carbon and if you had a beta minus decay, you would wind up with nitrogen, right? Because it's going to go to the thing that has 1 more proton, which means you're going to move up. Now the mass doesn't change, because we're considering the mass of neutrons and protons to be the same, even though I just said neutrons weigh a little bit more than protons. But the difference is so small that when we count the A number, we don't worry about the difference, and we count them the same. So if you go, for example, from carbon to nitrogen, then you're still going to have the same number total of nucleons. And when I say nucleons, I mean protons and neutrons. But they're going to be arranged differently. In other words, for carbon, you'd have 6 protons and 6 neutrons, and for nitrogen, if you did this to it, and this is not the way nitrogen is in the chart, but if you did it this way, then it would change it so that it would be 7 protons, and then you'd have 1 less neutron, so it would only be 5. So it's because of that 7, the atomic number being 7 makes that nitrogen. Now, that's not a very good example for you to try to remember, and the reason is because it's not something that's really going to happen. But I'm just using that to kind of point out that what we're doing here is we're taking a neutron and turning it into a proton, and then an electron, where the electron is then sent out of the atom. So it goes off into space. So here's an example that we can actually use. So we're starting off with atomic number 90. This is thorium, and it's decaying by beta minus decay. We can tell that by looking over here at the right. That's a beta minus particle, which is just an electron. So it can be written either the way it is here is E with a 0 above it. The 0 means it has 0 mass, relatively speaking. It doesn't really have 0, 0, 0 mass. The mass of an electron is about 1/1000th the mass of a proton or a neutron, but compared to a proton or a neutron, it's 0, and the charge is -1. And you can also write this as a beta sign with a minus charge, and then you would put the same numbers, 0 and -1. So those are equivalent. These two are equivalent. So that's why it's called beta decay, is because the beta minus particle is given off. Okay, so notice this is important. The atomic mass doesn't change, but the atomic number goes up. So for beta minus, the atomic number goes up. Now remember I said there were 3 kinds of beta decay. One of them causes the atomic number to go up, and that's this one. The other 2, therefore, are different, so that means that they have to go down. So let's go ahead to the next slide. All right, so for the other 2, one of them is called electron capture, and one of them is called beta plus decay. So, I mean, beta minus was the one we just did, so this is beta plus. This one goes in the other direction. So instead of going from a neutron to a proton, you're going from a proton to a neutron, and in the process, you're giving off a beta plus particle. Let's actually use a real example this time, so we don't get wandering off in the wilderness. So here they're starting with 11 sodium. So here the atomic number was originally 11, and we do beta plus. So that means the proton in the sodium is going to turn to a neutron, which means that this atomic number will go down by 1. So notice it did that. So it went down to 10, which now makes it neon. So it converts it to a different element, which is kind of neat. But the mass number here, notice, doesn't change. So that's the characteristic of all beta decay. Whatever kind of beta it is, the mass won't change. The atomic number always does change, but the mass number never changes. And then this thing right here, notice that it's got a 0 mass here still, but that's a +1, even though it isn't written plus, it's plus, because there's no negative sign in front of it. And that means that this is not an electron. So be careful with that. It looks like it would be, but it isn't. It's a positron. So what's a positron? Well, a positron is just an electron with a positive charge, so it's considered to be antimatter. Okay, so here is our particle that's being produced, and that's what makes this, well, it isn't necessary that you have a particle for beta decay, as we'll see in a moment, but in this case we do have a particle. And then this is going to be our net result. So what you need to remember for this one is that you're taking a proton and you're converting it to a neutron. Now, and then also a beta plus or a positron. Okay, as you see that. Now, there's a problem with doing this, and that is that we said that neutrons are heavier than protons. So in nature, neutrons decay all the time into protons. But the opposite doesn't happen, because it's, if you want to think of it this way, it's kind of like endothermic. It requires energy. So whenever these decays get ready to happen, and there's some kind of a way that these nuclides just know they're supposed to do this at some time, and they always do it at that time, but energy would be required. Now, it's always there, because the energy could be coming from anywhere. I mean, even in a solid, you have enough energy just from the atoms in the solid jostling around, or from just the internal energy from it will be enough to push this thing forward. But just be aware that it will require energy. And then there's something else about this. Notice here, let's go back down here to our reaction that's written out. Notice that we're starting off with 11 protons on the left, and that means we have 11 electrons on the left. On the right, we have 10 protons, which means we're only going to have 10 electrons. So what happened to that other electron? So we've lost an electron somewhere, and it isn't this. It isn't that. So that means there's also, in addition to the beta plus here, there's also going to be another electron given off. So why didn't we write it? Well, because that's just not customarily written in there, but it's there. So let's put plus a regular electron. And so what we're actually doing, in essence, is we're producing the neon 22 with 2 electrons or positrons in addition to that. And so, I mean, even though they have different charges, it requires the same amount of energy to make them. And that's about half of what we call a mega electron volt, which I don't want to try to explain that right now because I don't want to get this thing too long. But it takes about half a mega electron volt to produce an electron or a positron. So, but we're doing 2 here. So that means we have to have an energy input into the sodium 11 of about 1 MeV for this thing to happen. Again, whenever this thing gets ready to decay in this way, it will find that energy and it will go ahead and decay. but you should be aware of that this one will be the kind of thing that will require energy input, whereas the other ones that we talk about don't. All right, so the bottom line is that for positron decay, the mass, again, because this is a kind of a beta decay, won't change, but the atomic number will decrease. That's what you need to remember here. I mean, that's the main thing you need to remember. The atomic number decreases by 1. Now, there's another competing process with this that's more prevalent in lighter elements, and that's called the electron capture, which is abbreviated as EC, which we'll see on the next slide, or a couple of slides over, actually, because I talk on the next slide, I think, about the energetics of this, which we just mentioned. Electron capture, though, will have the same net result, kind of, but it behaves differently. So let's look next at the next slide and see about the energetics. So notice here, it says this requires about 1 mega electron volt in order to go, and 2 beta particles are produced, 1 regular electron and then the positron. So this is what we just talked about, and then it says that at the bottom, electron capture will compete with that, and the basic result will be the same. So let's go to the next slide. Okay, so back to the other one just for a moment. Whenever these positrons, these beta plus particles are produced, they don't last very long. I mean, the lifetime would be measured in nanoseconds, because as soon as they're made, they're immediately gobbled up by a regular electron. So what will happen is that the regular electron, which is our kind of matter, regular matter, will bump into the positron, which is antimatter, and they'll actually kind of blow each other to bits and produce energy, which will actually be in the form of 2 gamma rays, which is written down here. And then I say this is an example of mass being converted to energy. All right, let's go to the next slide. Electron capture will be the last one, you'll be glad to hear. So this is a different process. So what you have here is a nucleus with some electrons around it, which are like out here. And then there's a shell that's going to be the lowest, which will be the one S2 here, which I'll try to draw with this clumsy little device. And what happens is that a proton here in the nucleus just reaches up and grabs one of these electrons, and the proton and the electron go together to make a neutron, and that stays in the nucleus. So what's happening is you're out 1 electron down here, so now you've got a hole, they call it here. And so what will happen after that will be that one of the outer electrons will fill that hole by falling down from above it. All right, so what's happening is that we have a perfectly balanced equation here, because we're taking a proton and combining it with an electron, and then that's going to make a neutron, which means, again, the atomic number is going to go down because we lost a proton, right? So it's going to be the same thing that happens here that would happen with positron decay that we talked about just a few minutes ago. We're taking a proton, in essence, and we're converting it to a neutron. So when that happens, notice that the electron here is written on the left. I've got a feeling this is going to go over an hour, but it can't be helped. So you're taking one of the protons here out of these 80 mercury protons and adding an electron to it, and so it becomes a neutron. So even though it's changing from a proton to a neutron, you still have your 201 nucleons total, but you no longer have 80 protons, now you have 79. And then here, they've got gamma ray here, and you could have probably written that on every one of these, but the reason they wrote it here, I think, is because, well, I don't know why they did, to be honest with you. I think maybe it's because they're introducing it for the next topic, the next type of decay. All right, so a proton plus an inner shell electron gives a neutron, which leaves a hole there where that electron used to be. And so when that hole is filled, then that is called internal conversion. You don't need to know this. And when internal conversion occurs, that produces X-rays. So X-rays are produced this way. You get yourself an element that does this, which some do more than others, and you assume that a certain number of those elements are going to do this. And then when they do that, then the electrons above will have to fill the holes, and that produces X-rays. All right, so, and then as far as gamma rays are concerned, I'll I'll try to talk about that later. I'll try not to forget. The atomic mass does not change. The atomic number decreases by 1. So notice here at the bottom, it's not the same thing as beta plus, but it's almost going to give the same result. So what's the difference here? Can you figure that out? Think about what we said about the energetics for beta plus. What's different about this one? Do we have to produce 2 electrons in this one? No. So would this one be endothermic? I mean, that's actually not the right word. But would it require energy? And the answer is no. So, I mean, this one can just happen without any energy input. Next slide. Next. And then gamma rays are produced by any number of different processes, including all the different kinds of decay we just talked about, so I wouldn't worry too much about this. It doesn't change either number. It doesn't change the atomic number, and it doesn't change the atomic mass. So everything stays the same. You're just putting energy out, and that's just something that happens as in the process of these other things happening. So just remember, well, this might be a good time actually, since I'm getting ready to move on. How are they produced? So, I mean, you think back to 1311, we talked about how the different kinds of, like, not radiation, but light are produced. And that has to do with atomic electronic processes. Like, for example, if you have an atom and one of the electrons gets bumped up to an excited state, remember what we said? If it then falls all the way back down to n equals 1, it produces ultraviolet. If it falls to n equals 2, it's visible. N equals 3, it's infrared. So how are gamma rays produced? Well, gamma rays are produced in a similar fashion by the nucleons. So it's like the same thing that happened with the electrons and atoms can also happen in the nucleus with the protons and the neutrons. So basically the protons and the neutrons also are arranged in such a way that they actually do have a ground state, and they can get bumped up. Like when other things bump into them, they can get bumped up to an excited state. And when they fall back down, they produce gamma rays. Okay, next slide. All right, so let's look at this zone of stability again. So notice the neutrons are over here, right? So the things in this area means they have too many neutrons. The ones that are blue, they're unstable. So they need to convert neutrons to protons. So how do you do that? How do you convert neutrons to protons? Well, you use what? Beta minus decay. So you convert a neutron to a proton, and you keep doing it until you get from over here to this red zone. What about down here? You've got too many protons. So how do you convert protons to neutrons? Either one of 2 ways. You can either use electron capture, or you can use beta plus decay. Next slide. And then this is, don't spend a lot of time on this. So, I mean, you might see a problem where they ask you how did you get from U-238 to something like radon 222. And I have seen that, but it's kind of straightforward. So every time you have an alpha decay, it doesn't always have to be followed by beta exactly, but they tend to go in such a way that you can have like alpha, beta, alpha, beta, alpha, beta in some places. Then notice there's another stretch here where it's just pure alpha. So what we're starting with here is U-238, and we're ending up with lead, where it's going to stop because lead is stable. All right, so let's go to the next slide. Okay, good. Here's a concept check. So let's test your knowledge. Which of the following produces a beta minus particle? Which means on the right-hand side of the arrow, we need to have either something that says beta minus or something that says electron with a negative, not a positive charge. All right, so, well, here's an electron with a negative charge, but it's on the wrong side of the arrow. So this is electron capture. So A is out, B is producing a positron, C is producing an alpha particle, and D is producing what? Well, we've got a -1 here, and it's on the correct side of the arrow, so the answer should be this one. Let's go to the next slide. And it's starting to act up on me again. Come on, you can do it. Wow. Okay, there's our answer. Next slide. Oh, okay, great. Next slide. Next slide. Next slide. Okay. Another concept check. Which of the following produces some form of beta decay? So in this one, you don't have to have beta minus. You can have electron capture or beta plus. So let's go through these. What is this? So look at it for a second. If you want to pause it, you can. This is electron capture, right? So A is electron capture, but that is a form of beta decay, even though it doesn't have beta in the name. B, what's happening here? We're producing a positron, right? So if you want to pause these, because I can't really pause it because of the time. All right, so, but anyway, this one is also going to be, let me put a check mark here and a check mark here. What about C? What about C? No, right? What kind of a particle is being produced here? Alpha, right? And that's not beta decay. What about D? Well, we're producing beta minus particles, so this is beta minus decay. All right, so let me flip through the answers real quickly. So go to the next slide. Next. 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 There we go. Okay, so we talked about this just a moment ago. So this is from 1311, right? So remember, if you have an electron, this is an electronic process, not a nuclear process. So whenever you have an electron that gets bumped up to an excited state, once it falls back down, and that's shown here, it depends on what layer it falls back down to. If it falls to our level, if it falls all the way to n equals 1, then you've got ultraviolet. If it falls to n equals 2, you have visible. So you may remember that for hydrogen, it produces some characteristic colors. And that's for like 3 to 2, 4 to 2, and 5 to 2 will produce these particular colors here. So 3 to 2 is going to produce this color, which actually matches almost the color of my pointer. Let's see, 4 to 2 is going to be this kind of like whatever color that is, maybe turquoise. 5 to 2 is this one, and then there's also another one where you can either consider it to be from 6 or from infinity. And so this was called the Balmer series. Next slide. All right, this is super important. This is the electromagnetic spectrum. Notice here that sound is not on here because sound is not an electromagnetic phenomenon. So what we're doing here, and you can write them so that the frequencies are getting bigger as you go left to right or right to left, and you'll see it both ways. But whenever the frequency is multiplied by the wavelength, you get the speed of light. And I had to sit down. So if you look here, whenever the frequencies get bigger, the wavelengths get shorter. And I don't want to get into this too much, but if you take physics, when you study electricity and magnetism, this is going to be like the culminating chapter where you talk about Maxwell's laws. And then when you talk about this, so your key here, and I just don't have time to go through it, it's fascinating. And notice here in the middle, we've got the visible light right kind of in the middle, and then we've got UV and infrared on either side of it. And then these are the things that we just talked about, the X-rays and the gamma rays as you go in this direction. Cosmic rays over here are not really rays, they're just things that are coming in from outer space. And then if you go in the other direction, you get into all of the radio waves, which if you're a ham radio operator, as I am, then you really know a lot about this stuff. Medium wave here is going to be where your AM band is. There are ham bands that are scattered all through this whole area here, 2 meter, 6 meter, and so forth. Television and FM radio actually kind of occupy the same bands. So anyway, as you go to the left, you're getting wavelengths are going to be longer, and the frequencies are going to be less until you get all the way over here. And I'd like to spend like an hour just on this, but I can't. But when you get all the way over to the far left-hand side here, that means your wavelengths are huge. So like you can see this is like 100 million meters. That's one heck of a long wavelength. I'm right here. But the frequency drops down until you get to 60 hertz. Hertz means cycles per second. which, I mean, you know, that's pretty low, right? That's actually the frequency of the electricity that goes through your wiring, which you already know that if you took 1311 from me. So the electricity that goes to your lights and your radios and all that is actually going at 60 hertz. So the AC that's coming into your house is coming off a transformer, off of a high power, high voltage line, and it's filtered down and transformed down to 120 volts, and it's at 60 cycles per second. So, but that's another form of electromagnetic radiation. Okay, I can sense that I need to move on. So let's go to the next slide. Okay, so kinetics is what we talked about in chapter 14. It's first order kinetics, so you'll want to remember that. I mean, that's important. So this is going to be first order, which means what? Let's just review. We said that the rate law, the integrated rate law for first order, was logarithm of a sub t equals minus kt plus the logarithm of a naught. In this chapter, we're going to substitute nt and n naught. It's the same principle, and so for the sake of time here, I don't want to spend a lot of time on it because we still have a long way to go, even though I abridged this so much. Because, I mean, this is less than half the number of slides I had originally. But still, what we're going to do is we're just going to take it as just take it for granted that we can rewrite logarithm of at equals minus kt plus logarithm of a naught, that we're just going to rewrite that so that instead of using the concentrations of some substance, we're going to be using the number of nuclides. So we're just going to change the a's to n's. That's all. So instead of being the way I just said it, it'll be logarithm of nt equals minus kt plus the logarithm of n naught. N stands for the number of nuclides. However, regardless of whether you write that in terms of like the actual physical number of atoms, or if you write it, I mean, this sounds weird to say, but you could still get the same result if you just write it in the number of grams, because a certain number of grams of the same nuclide is going to wind up with the same number of atoms. So for this, it looks odd to do, but we can actually say the logarithm of some substance, instead of writing the logarithm of the actual number of atoms, we can write it in whatever it is in milligrams, as long as we do the same thing on the other side. And the same thing we could do it for grams, or we could do it for kilograms even, although you wouldn't, because you're never dealing with that kind of a quantity in this chapter. And then also the rate constant k, the minus kt part. Where does the k come from? Well, what they tend to do in this chapter is they tend to make you figure it out. So the formula is that k is the logarithm of 2 over the half-life. So what they'll usually do is they'll just give you the half-life and make you figure out the k, just to be obnoxious. So the logarithm of 2 is 0.693, so you just take 0.693 and divide it by the half-life. Let's go to the next slide. Next slide. In fact, why don't we go ahead and try to make up some time? Let's just go into the next slide. Next. So you can pause these other ones and read them if you want to. So here's what we end up with. So this is what I was saying a minute ago. Logarithm of n sub t is minus kt plus logarithm of n naught. And then you can rearrange this, and the way you would do that would be to take that last term and subtract it from both sides of the equation, so it would vanish on the right, and over on the left you get logarithm of nt minus the logarithm of n naught, which you can rewrite according to the rules of logarithms as the logarithm of the quantity nt divided by n naught. And that's what's done over here on the right. So it's the same thing. It's just rearranged. That's all. But it turns out that this form right here is very useful because we can use it in one of the work problems and also in one of the problems we're going to encounter in just a moment. So what we'll need to do is get this ratio, right? We need to get the ratio of the number of nuclides, or the grams or the milligrams of nuclides or micrograms after some time t has passed, related to the number that we had when we started. In other words, if we started with 10 and now we have 5, and because 5 have decayed, then our ratio would be 10 divided by 5. And then we would just take the logarithm of that, and then that will equal minus kt. And again, the k would be figured out by using 0.692 divided by the half-life. Next slide. Okay, and so here you might want to read this. You might want to pause it and read this, but it's the same thing I just said a few minutes ago. Next slide. And here again is your formula to find, well, actually, it's the formula to find k, because what you can do, it's really here finding t1/2. So they're saying, okay, if you want to find the half-life, you can divide 0.693 by the rate constant, but we may not know the constant. In fact, usually in this chapter, you won't know k, but you will know the half-life. So all you have to do is just flip these or transpose these two things, put k where the t1/2 was, and put the t1/2 where the k was. Next slide. So here's a good example. A first order reaction is 35% complete at the end of 55 minutes. What is the value of k? So what we want to do, we have to make a decision what we want to choose. So, I mean, this is a kind of an assumption problem. I'm going to assume that we started off with 1.0 at the beginning of this, just because it's the easiest way to do this. And now it's 35% complete at the end of such and such an amount of time. So what do we have to do here? And then it wants to know the value of k. So we're going to, actually, I don't really want to take the time to write this out, so I'll just say it. Logarithm of n sub t equals minus kt plus the logarithm of n naught. So what we have here is we have t right here in minutes. So we want everything to be in minutes, first of all. At the end, so this is going to be our t, and we're supposed to find k. So we'll have to do this like algebraically. So we'll leave k as a variable. And so what we need to know is what? We need to know two things. We need to know nt and n naught. And I'm just saying, I'm defining n naught as one unit. So what is nt? So let me come over here and write nt. What is nt going to be? Well, it's whatever amount of n that was originally present is still around after the 55 minutes. How much is that? You tell me. How much is left? Is it 35%? Which 35% of 1 would be 0.35, right? Is that what we write for nt? It turns out, no, it isn't. What we're going to write for nt is going to be 0.65 because we started with 1 and we've used up 0.35 of that. But that's not nt, that's how much we take away from 1 to get nt. So this 0.35 came off the 1. All right, so next slide. I'm going to have to kind of try to speed up a little bit. So what we're going to put right here is 1. And what we're going to put right here is 0.65. And what are we going to put for t? We're going to put 55 minutes, which means our k is going to have units of minutes to the minus 1. And then we just solve for k. And it turns out, and one of the reasons why I chose 1 here is because when you take the logarithm of 1, it's 0, and that whole term vanishes. Right, so we end up just with k, if you do a little rearranging here, equals the logarithm of at, which at we said was 0.65, so you take the logarithm of 0.65. Remember, whenever you take a log or a logarithm of a number less than 1, you get a negative number. And also there's another negative right there that's in the formula. So that's where that one right there came from. This negative right here came from the fact that we're taking logarithm of 0.65 and then just multiply these out and you get k is 0.00783 and the units would be minutes to the minus 1, which is what we need. Next slide. All right, so this I mentioned at the beginning. So notice here, these things are not really, really tiny, like hydrogen or helium, which we would consider for fusion. But they're also not like gigantic, like uranium, which we would be thinking fission. So if they ask you this equation right here, this reaction, and they ask you, is this fusion, fission, or transformation? Your answer is going to be transformation. Okay, so try to remember medium transformation. Here are some other examples. It's telling us also here, Rutherford, this guy was involved in a lot, is the one that discovered this, which I don't have time, unfortunately. Next slide. Let's just talk for about 1 minute about particle accelerators like cyclotrons. Next slide, sorry. They can produce transformations, and what cyclotrons and other accelerators are basically just like for a cyclotron, it's basically just a kind of a D-shaped thing with a D on each side where you introduce charged particles into it, and the fact that they have these positive charges, you can use the positive charges as a kind of a handle to grab hold of them and start slinging them around. And the way you do that is by introducing them into a magnetic field. But cyclotrons and other accelerators don't just have magnetic fields, they also have electric fields, and they're at right angles to each other. So let's look next slide at a picture real quick. Next slide. So you introduce a positively charged ion in the middle here, and you turn this one over here. I didn't mean to draw that line. Okay, so you turn this D negative initially, and this one positive. So these are electric fields. The magnetic fields are going to be up here and down here. If this is negative and this is positive, and it's going to be attracted to the negative charge, so it will move in this direction. It will also be repelled by this. But once it gets to about, it starts here, once it gets to about right here, they switch it, and this becomes positive, and this one over here becomes negative. And then that means the particle says, oh, wait a minute, I don't want to go this way, I want to go this way. But as it goes, it's going to increase in velocity because of these fields that are acting on it. So that means it's going to move a little bit further out every time it does this, and you just keep switching it, switching it, switching it, switching it. Every time you do that, it will move further away, and it will go faster until it gets to the velocity you need it to be at, and then it will go right out the exit and go into a long, kind of like a pipeline looking thing, where the pipeline is surrounded by electric and magnetic fields, and that allows you to guide it, and then they'll guide it to a target somewhere, which would be in a different location. Next slide. Here's another picture. This is in a linear accelerator, and it's the same principle, except that you don't have the D's. So you start off with this one right here, positive, and then this one would be negative. And you have, I'm sorry, that's wrong. This one would be negative, and this one would be positive. Let me mark out that plus there. So when it first comes in, it's going to be plus charged, and it will be attracted to the negative here. So it will move in this direction, and when it gets to be about right here, then they'll switch the voltages, and now this one becomes negative over here, and so now it's attracted to this one and then this one. But every time it goes to another step, it's going to be moving faster. Next slide. Oh, I didn't mean to do that. So what you saw for just a split second there was Fermilab, and that was a picture from above it. And it was in the shape of a huge circle that's like, I don't know, kilometers long. But that's actually not a cyclotron, it's actually a linear accelerator, and this is what it looks like on the inside. So you can see they just have a very gentle curve, but it's still linear. And this is what I was talking about, the way the pipe's looking. I've got to move on. But so the ions here are going to be moving right through the middle of this pipe, and these things around it are giving it a charge electrically. There's an electric, not a charge, but a field, electric field and a magnetic field, and that's how they guide the stream of particles. Next slide. Okay, so I mean, we could have said a lot more about that, but just for the sake of time, let's go ahead and move on. Measuring radiation levels, I don't want to spend a lot of time on either. So basically, there's two different ways you can do it, or at least that we're going to look at. There are scintillation counters and there are Geiger counters. So for a scintillation counter, you're basically using the fact that some things will flash light when you expose them to radiation. So for example, let's see, what is it? Not zinc oxide. Well, zinc oxide might work. Also, I think, anyway, I don't think it's zinc oxide, but there's another kind of oxide that has the property that if you if you expose it to radiation, it will flash light, I mean visible light. So what you can do is set up a detector that can measure how many of those flashes or what the amount of light is that's produced by those flashes, and then measure it, and then it can convert that to tell you what the level of radiation is, what the radioactivity level is. So this would only be used in a situation where you're around something that's radioactive, like if you're prospecting for uranium, or in like the cyclotron laboratory where you're around radioactivity. So it uses the principle that certain things will flash when they're exposed to radiation. So that's not too difficult to understand. Geiger counters also are not too difficult to understand. They use a noble gas like argon, and when we did 1311, I mentioned when we talked about noble gases that they do have uses even though they don't react. They can be used in things like smoke alarms, and also they can be used in Geiger counters because they're stable. What will happen is if you take a chamber and fill it with argon, then if it is exposed to radiation, what will happen is that the radiation will ionize it. In other words, the radiation will knock off an electron temporarily. Now, the electron will eventually find its way back, but while it's off, you have a positively charged ion and you have a negatively charged electron floating around free in that chamber. And so what you can do is you can actually make a circuit that you leave deliberately open in the counter. And when you see that you're exposed to radiation, what will happen is the radiation will knock some electrons off, and those electrons can temporarily complete the circuit and set off either a light, or if you have it set up to some kind of a speaker, you can have it set up so that you can put it to an amplifier and then have it make a noise. So that's like in the old Western movies where they're out with Geiger counters, right? All right, so let's look at that next slide. So the Geiger counter here, we're seeing the reaction that happens here. The argon is in a gas form, and when it's exposed to radiation, the radiation will knock an electron off here, and that electron, let's go to the next slide, will allow this open circuit right here, which is not going to be a complete circuit ordinarily, to be completed just for a moment. And when that happens, then it will set off either a sound, or it can cause a deflection in the needle, or both. Okay, and then let's go to the next slide. Scintillation counters, zinc sulfide is what I was trying to think of. So I said zinc oxide. So sulfur's right under oxygen, and it's going to be the same chemical property. Zinc sulfide will give off light if it's hit by radiation. So let's read just the last sentence. A photocell senses the flashes and measures the number of decay events. And when I was at the cyclotron, we used scintillation counters. They did have Geiger counters, but they were only hung outside the doors of the caves, so that if you thought you got yourself some radiation dosage, you could come out, close the door, and then take the Geiger counter and see if you did indeed get exposed. Next slide. And then all I'm going to say about carbon-14 dating is it's used to date things. And the other thing I'll say about it is that a lot of people don't put much confidence in it. Let's go to the next slide. Okay, now this is the hard problem in this chapter, one of them. But once you understand, and one of the reasons it's hard is because it's just so long. But once you understand how to do this, it's not so bad. Now, so we'll go through this one, and then in the work problems, we have another one just like this with one little exception, which I'll mention. And so I don't know if I really want to take the time to read this whole thing. So if you want to read it, why don't you just pause the video? I'm just going to go right to the point here and point out a couple of things that we really need to know. First of all, here they're giving us the half-life, so we can use that to find K. The equation that we want to use is this equation from chapter 14. We're going to convert it to this form because we don't want concentrations, we want numbers. Remember, whenever we've got n's and naughts and nt's, we don't have to write the numbers in. We can write grams or whatever. In this case, it will actually be the numbers, though. Okay, so what they're saying here, let me just sum this thing up for you, and at your leisure, you can read this. We want to use this equation that I just underlined. K is going to be 0.693 divided by that number right there, which means we're going to get the K in units of what? Years to the -1, right? So we're going to be dealing with years exclusively. What we need to know is this part right here. The T thing is what we're trying to figure out over here. So we need to find the ratio of the N at the time we're dealing with this thing compared to the number that we had initially. So the bottom line here is that they're saying that the ratio of the ones that we have changed to lead, these, to the ones that are still uranium is 0.115. Now let me just explain this. What this means is that originally we had a certain number of uranium atoms, and in the process of time, some of them have converted all the way down to lead. Some of them, most of them, are still uranium. What we need to know is how many did we start with and how many do we have now. And so we can figure that out from this information they gave us, but it's not really like something you can just glance at. You have to do a little thinking. So what they're saying is that for every, basically, if you just want to choose 1,000, you don't have to. Let's say you use 1,000 here to be the number of U atoms that are still there, then that's going to be your NT, right? But how many did you have initially? Well, you would have had the 100. So if you choose this to be 1,000, then what you're saying is that you're going to have 115 of these. Now, let me say it again. If you choose your number here for U, and you can choose, you don't have to choose this, but it's easier. Let that be let that be 1,000. Then this would automatically have to be 115, because the ratio of the leads to the uranium is 0.115. So what that means is that 115 of these uraniums have changed over to become leads. What that means is at the beginning, we had the 1,000 that we have now left over. So the 1,000 that we chose is going to be our NT here. And if you chose a different number, you're going to get the same result. This is our NT. But 115 of the original ones converted, so we had to have had another 115 at the beginning, which means that we started with 1,115. So we added 115 we would have to add 115 to get how many we had initially. 115 of those initial number converted to lead. So the initial number would be 1,000 plus 115. So 1115 would be our N naught. So we can write that below in the ratio into, so this is going to be N naught. And I'm already over an hour. I can't believe it. Where does the time go? I won't say time plus when you're having fun for you guys, but so N naught is going to be 1,115. NT is going to be 1,000. So we're just going to stick those numbers in right here, where this N that they've got on the top is actually supposed to be NT. So NT is going to be 1,000, and there you go. I mean, the N naught below it is going to be 1115, and you're basically there. So, I mean, the whole hard part of this problem is, first of all, to read the silly thing, and then next to figure out what's your N naught and what's your NT. So once you've done that, you're done, because now you've got logarithm of 1,000 divided by 1,115 here, and it'll be on the next slide. So this is going to be 1,000 over 1115. So just divide 1,000 by 115 and then take the logarithm of whatever you get, and then set that equal to minus KT, where you know what K is. It's 0.693 divided by 4.5 times 10 to the 9th years. So if you know all of that, then you can find T. Next slide. The next few slides are just going to explain what I just explained, so let's go to the next one. So what we're going to end up with here is we're going to end up with NT over N naught is going to be 1,000 over 1115, which is 0.897 roughly, and take the logarithm of that, and that's going to equal, which they didn't write what that is, but it's going to be some negative number, right? Equals minus KT, which is minus KT, and this part right here in parentheses is where they're figuring out what the K was by dividing 0.693 by the half-life, and they get T is 7.1 times 10 to the 8th years. Now, we have another problem that's very similar to this in the work problems, except that they actually give you this ratio. So you don't have to go through all of this elaborate thinking to figure out what the ratio would be. It's just given to you. They just tell you basically that the ratio of the ones that are still around compared to the ones that you started with is blah, blah, blah. And so you just put that right in there instead of having to do all those calculations and then take the logarithm and you're done. Next slide. Man, I can't believe we're at an hour and 5 minutes already, so we're going to have to move along here. Radio tracers, so for the rest of this stuff, except for when we talk about the mass defect, I'm going to kind of speed up. Radio tracers is like when you go to the doctor, if you ever have, and you you have some problem and they want to get the diagnosis, so they put some kind of a radioactive element into your blood or whatever, or they can put it into your stomach. And then they can just watch it on an x-ray machine to see what happens to it and see if there's some kind of an abnormality. Next slide. So that stuff that we just talked about in this slide right here, I doubt you'll ever see this on a test. In fact, I can just about guarantee it. But anyway, here are some examples of this. So let's go to the next slide. Energy and mass. All right, this one's kind of important. So when a system gains or loses energy, it also loses. And let me stop here for a second and hold on 1 second because I've got to. Okay. I want to slow up just a second here. Whenever a system gains or loses energy, it actually, even though you wouldn't think about it this way, it actually also will lose or gain energy. It's just that when we do reactions in the chemical laboratory, like we can measure the changes in mass easily, but not the changes in energy because they're so tiny. So it's only when you're dealing with this chapter's reactions where you actually have very, very large amounts of energy that are being put off or whatever, that the or mass being converted to energy is such a great amount that you actually have to worry about it. So the relationship between mass and energy that we talked about previously when we talked about the two gamma rays and also electrons and positrons annihilating, the relationship is given here as the energy is equal to the mass times the speed of light squared, where the speed of light here is going to be 3 times 10 to the 8th meters per second, and the mass has to be in kilograms and the energy has to be in joules. So you're going to wind up with the correct units. It's going to be kilogram meter squared per second squared. Next slide. So I'll let you read this one on your own. Let's go to the next slide. Next slide. All right, here. This is another topic you could see a problem on the final, and almost certainly will see on my test. So this thing that we're going to do is called finding the mass defect. And it goes like this. Whenever you have, like, let's just say you started off with a helium nucleus and forget about the electrons. So you've got 2 protons and 2 neutrons. Think about it this way. If you separated out yourself, if you could do this like on a lab bench, where if you had protons and neutrons that were really huge, like let's say they're the size of marbles and you could actually do this, then what would happen would be that if you weighed the 2 protons and the 2 neutrons and added their weights together, their masses together, and then if you put them together to make a nucleus, I mean, it wouldn't work right because this wouldn't work the same way it does in an atomic nucleus. But if you had the same conditions you have in a nucleus, then when you stick those 2 protons and those 2 neutrons together to make a helium nucleus, and if you weighed it, it wouldn't weigh as much as the protons and the neutrons weighed when they were separated. Why? Because part of the mass of the neutrons and protons has to be converted to the binding energy. It has to be turned into energy, and it's that binding energy that's going to hold the protons and the neutrons together. So, I mean, there are all kinds of things we could say about this and how that's mediated. Pi mesons mediate that. But the bottom line is that part of the energy that you had, part of the mass that you had in the original protons and neutrons would have to be used up in order to form the binding energy. And that's true, like not just for neon, but for any element, any atom, like carbon. Carbon has 6 atoms and 6 protons. I'm starting to get tired. Carbon has 6 protons and 6 neutrons. So if you massed the 6 protons and the 6 neutrons when they were separate, and then if you compare that with the mass of a carbon nucleus, you wouldn't get the same number. Because again, part of the mass of the carbon protons and neutrons would have to be converted into energy to make the binding energy. So you can do this for any atom in the chart, as I mentioned earlier. And it turns out that you can figure out the number of the change in the mass, and that's called the mass defect. And unfortunately for you guys, you have to do that. You have to be able to do that for the tests, but it's not hard. So what we need to do is just figure out what is the mass of the nucleus of whatever it is we're looking at, like helium. Let's just take helium. We would have to try to figure out what is the mass of a helium nucleus, not the atom, but the nucleus, which it turns out is very difficult to do. And then we would have to find the mass of the proton and the neutron, but we'd have to multiply each by 2. And it turns out that we already do know what the mass of protons are and the mass of neutrons. But what we're going to do is we're going to use that mass of neutrons, but not the mass of protons. And now I have to do a little bit of explanation here. In order to do this same process we're talking about for some of the larger atoms like copper, or let's say some atom let's just use one like O, which has 8 protons and 8 neutrons. Okay, O, in order to get rid of its electrons, it has 8 protons and 8 neutrons. So if it has 8 protons, that means it's got 8 electrons. To measure the mass of the nucleus, what you'd have to do is remove those 8 electrons, and that would be almost impossible. It would be basically impossible. And then the bigger the atom is, the harder it would be. I mean, it's hard enough for oxygen. It's hard enough just to get 1 off. So to take all 8 of them off, I don't even think it's possible. I don't know how you would do it. But it turns out that if you use a little mathematical trick, you don't have to, because just take the assumption that, okay, we're not going to be able to measure directly the mass of an oxygen or whatever nucleus. So what we're going to have to do instead is we're going to have to use a mathematical trick. So let's just use the mass of the whole atom, which we can find out readily. And then right next to that, like, okay, let's just take oxygen. Oxygen has 8 protons and 8 neutrons. It has 8 electrons. So what we can do for oxygen is, instead of writing it as mass oxygen nucleus, we can write it this way: mass of oxygen atom less the mass of 8 electrons. So just write the mass of the oxygen atom and then minus the masses of 8 electrons. And we know what the mass of the electrons is too, but it turns out we don't even have to use them, because what we can do on the other side is we can match that, or counterbalancing it, by, instead of writing, okay, minus the mass of a proton, we can write it minus the mass of a hydrogen atom, in parentheses, open parentheses, hydrogen atom minus mass 1 electron, close parentheses. So what you're doing there is you're going to have mass of electron on both sides of your equation. So for that, you would have to multiply it in the front of the parentheses by 8, because you're going to have to do it 8 times because you have 8 electrons. So the way that you do these is you subtract, which it seems like it should be in the other direction, and I understand that, but it isn't. You subtract the masses of the protons and the neutrons from the mass of the original nucleus. So to finish this example, the way you would do it would be, and it would be the same for any element, but for oxygen, it would be mass of oxygen atom, in parentheses, all of this in parentheses, mass of an oxygen atom minus the masses of 8 electrons. And that is on the left side of the equal sign. And then equals, no, I'm sorry, not equals, but minus, sorry, minus 8 times the mass of a hydrogen atom minus, and this is all in parentheses, the mass of an electron. In other words, so you wind up with 8 open parentheses, mass of a hydrogen atom minus mass of electron, close parenthesis. Okay, and then for the neutrons, you just put minus the mass of 8 neutrons. So let's go to the next slide and look at this. Next. Next. And next. So at least we got through a bunch of this stuff. Okay, so let's go through what I just said again now. So this is the way you write what I just said. It's delta M, that stands for mass defect. Okay, so try to remember that stands for mass defect. It's the mass of the helium nucleus, so now we're doing helium, minus the mass of 2 protons, minus the mass of 2 neutrons, or the way they have it written here, you wind up with a plus sign because they've got the minus in front of a bracket. So the way that we're going to write that for any element would be that the mass defect is the mass of the atom. So look up helium in the chart, 4.0026, and then minus the masses of 2 electrons. So that converts this helium atom to a helium nucleus because you're subtracting its electronic masses. Okay, so all of this is going to be on one side, and then minus the masses of the protons and neutrons. Well, for the neutrons, you can just subtract minus 2 times the mass of a neutron, which is 1.0087 AMUs. But for the proton, if we write it this way instead of just writing in what it is, we write the mass of the atom, which is 1.0078. Again, look at the chart, and then write it minus the mass of an electron and leave it written that way. Multiply it by 2, because what you're going to wind up with here is you're going to wind up with a mass of 2 protons anyway, because if you take an electron away from a hydrogen atom, you have only a proton left. But if you do it this way, you're going to wind up on this side over here with a minus here times a minus, which means plus 2 times the mass of an electron, and over on the left-hand side, we've got minus 2 times the mass of an electron. So a minus 2 ME plus 2 ME is 0. In other words, what's going to happen is if you do it this way, you're going to cancel this one and this one. And what it means is that we don't have to worry about trying to measure the mass of a nucleus. We can just choose the atom's mass and then subtract away the appropriate number of electrons, and then it works. All right, so let's just take the case that you get a problem on the final exam where you're asked to do this. So they say find the mass defect, and they want you to do it for carbon. Well, the only difference would be that you would look up carbon, which if you do that, I can tell you what you're going to find. You're going to find 12 because they set carbon deliberately at that number. So carbon 12, if it's carbon 12, anyway, or if you want, whatever the thing is, just look it up on the chart. So, I mean, not all carbon is carbon 12, so they would have to tell you if it's a pure isotope or whatever. If they just tell you carbon, because carbon is in 3 different isotopes, so I think if you look at the chart, it's actually not 12, it's 12.01. But the isotope specifically, I don't want to confuse you with this, but anyway, just look it up on the chart. Okay, so just write 12.01. Unless they tell you specifically it's carbon 12, and then you would want to use only whatever, but I'm pretty sure that they won't do that. So just write down whatever it says on the chart. So that is the atomic mass of carbon, and then subtract 6 electrons because carbon has 6 protons, so it would have to have 6 electrons. So it would be 6 times the mass of an electron. And that's what's going to go on the left. So if it were nitrogen, it would be the mass of the nitrogen atom minus the mass of 7. If it were oxygen, it would be the mass of the oxygen atom minus 8 electrons. And then over here, you'll subtract the appropriate number of neutrons over here. So whatever it is, 6, 7, or 8, just multiply that by the 1.0087. And then write 6, 7, or 8 here. in front of the 1.0078, which is the mass of hydrogen, minus, and then this number here, instead of being 2, would be 6, 7, or 8. Okay, so once you do this, then you get here a number of minus 0.0304 AMUs. And that is your mass defect. That's your delta M here. Okay, so that seems like a lot of work, and the first time or two you do it, it is, until you see the pattern, and then it just becomes really easy. So usually what they'll do is they'll say, okay, find the mass defect, and then they usually, maybe not always, want you to convert that to binding energy. So that's easy. All you do is use E equals mc squared. So you would just start off with this number and take the absolute value of it, because you have to have that, because you can have a negative amount of energy. So you would convert this to plus 0.0304 AMUs, and then you have to multiply that by whatever the conversion factor is to convert this from AMUs to kilograms, because you want this in kilograms. So you would have AMUs on the bottom and kilograms on the top, and the conversion factor, I think, is 1.66 times 10 to the minus 27th, so that would go here on the top, so 1.66 on the top times 10 to the minus 27th. I'm not going to write it all out. And then you would have a line here per 1 AMU. So multiply 0.0304 times 1.66 times 10 to the minus 27th, and that will actually give you your delta M in kilograms. And then just say, okay, E equals mc squared. So E equals mc squared, where the mass would be whatever you got over here when you multiplied this number right here times your conversion factor, and it's going to be in kilograms. So write that here, whatever it is, fill in the blank, and then multiply that by the speed of light squared, and you're done. Speed of light is just 3 times 10 to the 8th meters per second. Square that, multiply it by your kilograms, and you're done. Next slide. Next slide. All right, so when we did that problem, we got 0.0304 AMUs, which when I converted it using this conversion factor, I got 5 times 10 to the minus 29th kilograms. Multiply it by 3 times 10 to the 8th squared, and you get 4.6 times 10 to the minus 12th joules. And that is your binding. That's called the binding energy. So, okay, that's how you do these problems. Okay, so again, if you had some atomic number, say of 50, that was 25 protons and 25 neutrons, then you would say, okay, look it up in the chart. Let's say you look it up and it's 50.06. Then write that down, and then write minus 25 electron masses, and then minus, and then if you want to put it all the rest of it in brackets, it would be minus 25 times the mass of a neutron, which you can just use the number, which is 1.0078. And then minus 25 times the mass of a hydrogen atom less the mass of an electron, right? So you're going to start off on the left-hand side with the mass of 25 electrons. It's actually negative. And then you're adding plus the mass of 25 electrons on the right. And they cancel. So they all work the same way. So the bottom line is what you need is the mass of the atom off the chart on the left, and then you have to figure out how many electrons it has by, it will be the same as the number of protons. So look at the bottom usually number, the Z number, or the lower number, and that's the number of protons. It's going to be the same as the number of electrons. So that's how many electrons you need to subtract on the left and add on the right. Then just add that number of hydrogens minus the mass of an electron. I think I've said enough about this. Let's move on. So let's just move on. For this chart, I'll let you look at this on your own. What they're doing here is they're just figuring out the binding energy as we just did a minute ago. And then they're saying, okay, let's divide that energy, the total amount of energy, by how many nucleons. In other words, let's divide it by how many protons and neutrons we have. So that's what they do here. And they found that iron 56 here is the one that has the highest binding energy per nucleon. I don't think you're ever going to see this on a test. You could on the final, because sometimes the people that write the finals get flaky. But when they did this, they plotted these, and you can see that the one that had the highest binding energy per nucleon was Fe56, and which you could also say it's the most stable. Let's go to the next slide. All right, we've already mentioned this, so just very briefly, when you have two very light things, like here we've got helium-3 and hydrogen-1, and they're joining together to make this. This is something that happens, I believe, in the sun. It's called fusion. So they might ask you this on the final exam. They might say, what kind of process is this? So remember, when it's really light particles, it's fusion. If it's something really big like uranium, it's probably going to be fission. In fact, it is going to be fission. And if it's in the middle, like say nitrogen going to oxygen, then that's going to be transformation. Next slide. Let's talk about fission. Next slide. Whenever you have like uranium and you hit it with a neutron or whatever, it can split, and a lot of energy is given off. So that's the basis of nuclear reactors. You can look at this if you want. Next slide. So let's just read this. Nuclear power plants operate by causing a chain reaction to induce a controlled rate of fission. And notice the key word here is controlled. You don't want it to get out of hand. The fission process alternates between being subcritical and slightly delayed supercritical. I'm not even sure exactly what that means. The reactor needs to be able to hold the reaction rate, so this is the key, needs to be able to hold the rate fairly constant in order to be useful and safe. So the way that they control it is whenever it starts to get a little bit too hot, they put a rod called a control rod into the reaction core, the reactor core. Let's go to the next slide. And so you can see those over here. So these rods can actually block the reaction from proceeding any further if you push them down. So these things here in yellow or gold are the things that are actually reacting, and they're producing an enormous amount of heat. And if you want, it's kind of an interesting thing to look at how this works and how it produces, the heat produces steam, and then that steam goes out and drives a turbine, and that's where your power comes from. So this works kind of like an old steam engine, which we don't have time to talk about, but in the old days, before they had the diesel engine, they had the steam engine, where you see it in the old Western movies where the guy's shoveling coal as fast as he can because they're trying to get away from the bandits. And as he shovels the coal in, the heat increases, but then that's in a separate container away from where the actual gears are, which would be up in the locomotive where the conductors or whatever, the operator is driving it. So that would be the same thing here. The nuclear power is produced here by this radiation, this fission reaction, which puts off a ton of heat, which heats up this water, and the hot water goes through some other water and produces steam, and then the steam is used over here in a different compartment to drive a turbine which produces electricity. Anyway, the thing I really want to point out here is that these things are supposed to run fairly hot, but not too hot. So what has to happen is somebody has to watch it. They probably do this, I'm sure they do this electronically, but there's got to be an operator there too. And then whenever it gets to be just a little bit too hot, then they'll push the control rods down, and that will slow the reaction a little bit. Let's go to the next slide. And here is a close-up of that. Next slide. All right, and then this is the one other thing that you could see a problem on. I know we're almost out of time, so I'm going to go through this kind of quickly because it's not hard. So there are 4 different ways that radiation can hurt you as a human being. The more energy it has, then the more likely it is to do damage because it's going to be putting more energy into your flesh. The penetrating ability is also important because the further it can penetrate into your body, then the more damage it can do. And so that means that gamma rays are going to be much more dangerous than anything else, especially alpha particles, because gamma rays can go through just about anything unless it's pretty thick, except for lead. So that's why they use lead to shield those caves. And also the ionizing ability, which is, almost all radiation can ionize, but especially gamma rays can ionize things. And what that means is, as we said before, it just means to knock off an electron and produce a positive ion. And then also, this one doesn't always apply, but sometimes chemical properties are important. If it's the kind of thing that if it were accidentally eaten, if it has the same chemical properties as, like for example, something that your body would typically use, then that would even make it more hazardous. Next slide. So let's very quickly close this up by talking about how we can measure the amount of REM radiation you've been exposed to, and then we'll talk more about it in the work problems. So the units of radioactivity would be that 1 becquerel is 1 disintegration per second, but it turns out this is not particularly useful because it's such a small number. So most of the time we use a curie to measure how strong the radiation is. So it'd be like, that is 3.7 times 10 to the 10th disintegrations per second. As far as the thing that we're going to focus on in this last section, 1 rad, and you'll see this a lot in the news, is defined as, let's forget this first definition and come over here, it's 1 times 10 to the minus 5th joules per gram of your tissue. So however many grams you weigh, whatever radiation you're exposed to, you would divide that, and you would divide the 1.0 times 10 to the minus 5th joules per gram would be defined as 1 rad. So I mean, let's just take the simple example that you have something that is a living organism that weighs 10 grams, and let's say you exposed it to 10 times 10 to the minus 5th joules of radiation. Then you divide the 10 times 10 to the minus 5th times 10, and you get 1 times 10 to the minus 5th joules per gram of its tissue, which means that it would have been exposed to 1 rad. But that's not the only thing we need to consider, so let's go to the next slide. We also need to take into account how effective this stuff is that we're exposed to in causing damage. And that's going to relate back to the slide we saw just a minute ago where you kind of like approximate the damage that it can do based on how far it can penetrate and how well it can ionize and so forth. So when we do that, we call its effectiveness in causing biological damage the RBE number. So that's, I think it's radiation biological effectiveness. So once we know that, and that will be given to you if you have a problem on this, which you probably will, this number right here, the second number, would be given to you where you would have to figure out this number. So we'll see that. And then when you multiply the rads times the RBE, you get what are called REMs. And this is kind of like what we're looking for so that we can look this number up in a chart and see how bad it was. So the number of REMs is our final destination. So let's go to the next slide. So here's your chart, which you'll need to do some of the problems. If it's 0 to 25, it doesn't really matter. And these doses, notice, are in REMs. So 0 to 25, you don't have to worry about it too much. 25 to 50, unless you're going to be exposed to it all the time. 25 to 50 will actually produce a temporary decrease in white blood cell counts, which means you're more prone to what? Infection. 100 to 200, you're going to have a strong decrease in white blood cell counts. And man, if you get exposed to 500 REMs, you're in big trouble. So I'm thinking probably when we had this Fukushima thing, probably a lot of those guys that went in there and worked in there probably didn't have any particular reason to live very long, and they wanted to make a lot of money, which they were paid a lot to do it. They probably just made the money and gave it to their family and then just kind of went away. Next slide. All right, so we'll have a problem in the work problems where we'll actually do one of those, and that's kind of fun. Let's wrap this up now. We're over an hour and a half, so I'll see you in the work problems.